This video is hopefully going to answer two questions. The first one being, why do we bank the turns going from, like, say, an interstate to a highway? If you've ever seen those large interchanges, like maybe you have your highway coming in and there's another highway going across. And we get these big looping interchanges, and they crisscross and all sorts of stuff. So how do we safely do that and kind of maintain our speed so that way the traffic can flow? Because, I mean, if we're going 70 and we're about to join something else going 70, we need to be able to turn at relatively the same speed so we can join up with the rest of the traffic safely. And the way we do this is by banking the turn. So if you've ever seen like a NASCAR race, most of the tracks tend to be elliptical. So at the bottom there's an oval, but around the track at the ends, since they're going at such a high speed, if this is like a cross section, the whole thing is banked. The cars are moving not on well, it's on a flat surface, but it's not at a horizontal surface. The turns are being made at an angle from the horizontal. So you got these cars that are coming around. Okay. And what I want you to realize there is, since they are turning, if they're not like sliding up or down, we can kind of think of them as their turn as part of an arc of a circle. It's just that the circle is above the ground by some measure, but we don't really care. So let's say we know the radius of the turn and we know theta. Maybe I want to know, this goes back to our example of the warning signs for turns. So maybe I want to know the speed that the car can go at without worrying about having to need friction to prevent it from sliding up or down the incline. So what's a safe speed to go at without having to worry about skidding? So let's go ahead and draw our free body diagram. We'll have the weight pulling down. The normal force is now at an angle, and it may look like we don't have centripetal force, but notice that normal force has an inward component. So we can set this up as the centripetal force is equal to the horizontal component of the normal force, and the weight of the car is equal to the y component of the normal force. Now, if you have seen the rest of my videos, you know one of my tips for solving forces problems is to make your acceleration positive. Let me fix the free body diagram here. Remember, no components on a free body diagram. Since the acceleration is inward, I don't want to rotate my axis like I would on a typical inclined plane problem. So we aren't going to rotate our axis here, which means that we need to resolve the normal force. So normal force this way. We're going to have the y component here, which will be equal to mg, and the x component here, which will be equal to the centripetal force. Now we got to figure out where the heck theta comes into play here. So this is our bank. We have mg going down this way. And the normal force here is perpendicular to the surface. So we can extend the normal force out as well. And hopefully what we see here are that these two angles should be congruent if we know our geometry. And if you remember from inclined planes, this angle here was theta. As we tried to break the weight into its components. So if this angle down here is theta, geometry tells us this must also be theta. So let me clean that up. And now we can take our two equations and kind of start substituting. So we get mv squared over r is equal to the x component of the normal force, which is normal sine theta. And we have mg is equal to normal cosine theta. We don't know the normal force, and we can substitute if we want. Normal will be mg over cosine theta. So let's go back over here. mv squared over r is equal to, whoops, mg sine over cosine theta. What? We don't care about the mass of the car, and we're back to tangent theta again if you've watched the conical pendulum video. So we get v squared over r is equal to g tan theta. So to safely go around this turn without having to worry about slipping or sliding, or at least needing friction to prevent us from slipping or sliding, we get that the safe speed is root ger tan theta. And you may be asking yourself, why are we getting the same speed that we would for a conical pendulum at that radius? Well, look at the free body diagram. They're the same free body diagram. So we should get similar answers. And what this tells us about those swings, the tower swing, if you watched that video earlier, you're sitting in a chair. So we can, when we're designing this, we can figure out a speed that will allow you to sit in your chair without having to worry about sliding one way or the other in your seat. Granted, that speed may not be possible for some designs, just because that speed may make you sick. I don't know, but that brings us back to conical pendulums, but not quite. How we're able to change highways speeds, or not, it doesn't answer why we can change from one interstate to another interstate, or one highway to an interstate, whatever, at such a high speed. It kind of because we don't always go the right speed for that turn. So let's take a look at what happens when we don't. So I'm going to clean this up real quick. So let's say we go too fast for our turn. Are we going to slide upward or downward in our lane? Well, remember centripetal force here. The faster we go for the same amount of centripetal force, we'll have more momentum. So we'll want to stay on our tangent line. That would take us out of our circle. So the faster we go, the further out our momentum will carry us. So we would be sliding upward. Well, if we're sliding upward, that would mean that the friction is downward. So let's think about this here. Our centripetal force, which is mv squared over r, the faster we're going, in order to maintain that radius, our centripetal force has to increase. Well, take a look here. Now not only do we have the normal force pointing inward, but we also have the frictional force pointing inward as well. So it'll help keep us from sliding out. If we go too slow, we would slide down. And in that case, the frictional force that friction force would push upward on us. And it would have an outward component. So we would have less centripetal force for less speed. So even if we don't go the exact right speed, that friction there will help us stay where we are, or at least stay in the turn. And we can think of what the net force would be if we're going too fast. The net force would be the x component of the normal force, or the horizontal component, plus the horizontal of the frictional force. So in cosine theta plus, oh, it gets worse. I goofed 1 second. Notice though, we have a downward component. Oh no. So that would increase the amount of normal we're going to experience. So we're actually going to have several equations here. So mv squared over r is equal to the x component of the normal force. So in cosine theta plus mu times our normal force. And we'll want the horizontal component here. So if this is theta and this is theta right here, this would be 90 minus theta. So that is also theta. So this would be in cosine theta. And our y here, we would get the y component of the normal force is equal to mg plus mu normal times sine theta. And we can rewrite this as normal sine theta. You see it gets a little bit hectic, but if we're going too slow and the friction points the other way, it's a quick easy change here. We can just subtract the friction. But that system of equations will allow you to solve for the variable that you need. We can even get rid of the normal force if we wanted. Hopefully you can see that you could factor it out right here and plug it into the next one. But yeah, that's how we can change from one highway to another while still being able to go at a pretty fast speed. We have the normal force pushing us in and the frictional force if we need it. And that's all I got.